All right, thanks. Welcome to the, it's amazing to see. It's been like a year and a half since the first workshop, and it's just amazing to see the uptake. Every time I'm completely underestimate what's going to happen the next time. So this has been amazing progress. Another thing is kind of fun to sit here, and I think it's been 9 years since I gave a lecture in one of these, rooms, and they haven't really changed much over that time. It's kind of fun to be back. So today I wanted to, it's great to have Rick running the organization. I can now go back and focus on more technical stuff. So you saw last week released the 1.9 version of the privileged architecture. So I'm going to just walk through our thinking on how we designed the interrupt system. This is something we haven't really talked about before. Obviously a very important part of any real computer system. So when you look at interrupts, they're used in different ways in different application areas. And I think when I talk to people about interrupts, they often argue with me because they're thinking about one of these domains and ignoring the needs of other domains. So I just wanted to go through my view of the different ways people use interrupts. So in high-performance Unix-like systems, it's really interrupt handling should be a small fraction of the processing time. And the reason is you usually have pretty fast processors and pretty smart devices. They're actually offloading a lot of that work. And the real model there is you do minimal stuff in the handler. You package it up in a way that software can then go schedule it at its leisure outside of the interrupt handler. That's kind of the model of high-performance systems. Now, if you look at low to mid-embedded systems, the guys view things very differently in that space. It's, you're spending a lot of time in the interrupt handler. It's a significant fraction of the processor time. And the reason is you have a lot slower processors and a lot dumber devices quite often in the embedded space. The processor's acting as part of the device. And also, if you look at why do people worry so much about the interrupt controller? In the embedded systems, often that kind of is the task scheduler. You kind of put a lot of smarts in the interrupt controller to decide what the processor should do next. And that's a very different mindset than the guys building the high-performance Unix systems. Finally, if you're building really high-performance real-time systems, you don't take interrupts. You just occasionally, you have the heartbeat system, you have things queued up. You don't have time, because basically all your time is spent handling interrupts. That's another very different thing. And there's everything in between. So, I imagine I'd be curious to hear about things that don't fall in these categories and what people have been doing, but I imagine there's many, many other use cases for interrupts as well. But just to lay out the land so people don't get confused about which thing am I talking about, it's basically, for RISC-V, we really want to support all these kinds of systems. And one of the driving goals in our interrupt scheme is simplicity, like the rest of RISC-V. We also want to support everything from tiny embedded systems all the way up to massive supercomputers and hyper-virtualized servers. And want to also be flexible, enable implementers to trade off between implementation cost and performance. And also allow this specialization for given needs. Like one of the big goals of RISC-V is to give you a common base with good software support that you can then extend for any given application. We want to extend that model to the way we handle interrupts also. Okay, so let's sort of dive into how we think about things in RISC-V land. So we categorize interrupts into two kinds, local and global. So local interrupts are those that are directly wired to one of the hardware threads, the hearts, right? So in RISC-V terminology, we call a hardware thread a heart. And so the great thing about local interrupts, there's no arbitration figuring out who's going to take the interrupt. It's directly wired to one heart. You can easily determine what the source of the interrupt was. You have local control registers that tell you where the interrupt came from. And in RISC-V, to keep things simple, there's only two of these. There's the timer and a software interrupt bit, right? So there's two local interrupts per heart. Global interrupts are basically everything else. These are things that are routed through what we call in RISC-V land the PLIC, the platform level interrupt controller. And this arbitrates between there may be multiple recipients of the interrupt. They're going to arbitrate to get hold of that interrupt and service it. And the way you actually get hold of this is a memory map device. So the PLIC is memory mapped, and that has some implications I'll get to later, right? So it's shared by all the hearts in the system. So local interrupts, global interrupts. The way this shows up in the ISA, in the privileged architecture we have at the machine mode level, we have this machine interrupt pending CSR, the MIP, MIP. And as you see here, it has this is the local software interrupt, this is a local timer interrupt, and then you have external interrupts coming from the PLIC. And in each of these categories, you see there's a separate bit for each of the privilege levels, user, hypervisor, user, supervisor, hypervisor, machine mode. Right? Each of those is a separate interrupt pending bit. I'll get back to that later. there's a bunch of space at the top, and that's where you should add specialized local interrupts. If your system needs some fast local interrupt to that thread, that's where you add it. I've seen the mailing list. Some people have been doing that already. They figured this out. This was the goal, and that's you're spot on. That's what you should be doing, is adding stuff up here. We should probably spec out where we'll probably reserve a chunk of that for maybe there will be future standard other local interrupts, but the other piece will keep reserved for people adding their own stuff up at the top. Okay. One other thing I'll talk about today that we sort of introduced over the last few months is user-level interrupt handling. Now, this is something that does appear up at, it's an extension to user level, and we gave it the letter N for interrupt. And I'll walk through that, but basically it just parallels what we did at the other privilege mode level, so it just follows directly from the design at all the other levels, but adds this capability of doing user-level interrupts. And I'll talk a bit about that and why we think that's important, especially for embedded systems. Okay, so this is a global picture of the structure of interrupts. So you have hardware threads. They have different privilege levels: machine, hypervisor, supervisor, user. Each privilege level has its local interrupts, and each privilege level also has a connection from the PLIC, which gives it its external interrupt signal, right? And so the PLIC is responsible for taking external interrupt sources and routing them to the correct privilege level on each of the hearts in the system. Okay. So let's walk through the local interrupts. So software interrupts, these are things where the software can just set a bit in a register and cause an interrupt to happen. And so there are these 4 different privilege modes. So machine mode, the machine software interrupt bit, MSIP, that's the, you can only write to this through a memory map control register, right? And the reason is that this is how we do actual interprocessor interrupts in the real hardware on a real system. So only machine mode can get to these registers. They're memory mapped. And even when you're writing to your own MSIP, when a hard is writing to its own MSIP, it goes through the memory map control register. There's a bunch of reasons we did this. One is that that register probably lives a different clock and power domain in the processor itself, because it might be used to wake up that processor when it's asleep, for example. So that's the kind of real physical distributed across the machine available software interrupt source, MSIP. Now, stacked above that, you have the other privilege levels, HS and U. And a heart can only write its own SIP bit at those privilege levels and not another one. So if you're running on one heart and you want to set the supervisor interrupt pending bit on a different heart, you have to basically go down to machine mode across the machine and write it over there. And the reason for that is the other heart may not be running. It may be descheduled. You won't know that locally. So you have to go through the lower levels to get across the machine to find where this other context is, because it may be descheduled. Okay. So basically, the only way that you can do inter-heart interrupts is in machine mode via the memory map control registers, and everything else is basically virtualized in software on top. So this is the software interrupt bits at each privilege level. I'll stop and take questions at any point, actually. Okay, timer interrupts. So time is actually quite difficult, especially real-time timers, which is what we specified in RISC-V. The reason we fixated on real-time timers is these days processors run at variable clock rates. So a cycle counter is not a wall clock timer. So you need a separate real-time clock. That's usually what you want to schedule against. So the other thing is, if you have a real-time timer, it's probably, again, in a different voltage frequency domain from the processor itself. And usually these are quite expensive to provide, as actually having accurate real-time is costly. So there's usually only one real timer in a system. So the organization of the stack here was to simplify the implementations of this. So there's a single 64-bit real-time hardware timer that's only really available in machine mode. And the machine mode on a heart has a compare register, which is a memory mapped control register. It's memory mapped again because it lives over by the real-time counter in the hardware. And the idea is all the other interrupts are basically illusions created by the machine mode. It's going to prioritize the other timer interrupts the lower privilege levels want to do, and figure out the next earliest one, schedule its interrupt to do that, and then set the appropriate timer pending bit in the appropriate privilege level above that heart. Okay? So that's the way we model these other timer bits. Now, this is for the local high-frequency timer inside a heart. Now, on a given platform, you may have many other hardware timers attached via the PLIC. So you may add other kinds of real-time timers. out there. But this is just for the local timer. This primarily be used for operating system scheduling and those kinds of tasks. Okay, so those are the two local timers. So we talked about the pending bits. Those are where you can view the current status of the interrupts. There's also the interrupt enables, which is sensitizing the heart to respond to certain of those interrupts. So the MIE register is also, this is a machine mode, and it has the same, it mirrors the format of the IP register, and it just has a separate enable bit at every privilege level for every source of interrupt. That's pretty straightforward, pretty standard. And again, if you add additional ones, you would just add the enables up in the high bits here. So now mStatus is the status register of the processor. mStatus is kind of the heart of controlling the whole heart. And what you have down here in the low pieces of mStatus are the global interrupt enables. This is a single bit that globally turns on and off interrupt enables for the heart across the whole system. So we call these the global interrupt enables. And when you're running at a given privilege level, all the interrupts for any interrupts at a lower privilege level are automatically disabled. So you will never be interrupted by a lower privilege interrupt when you're running at a given privilege level. And you can never disable interrupts from any higher privilege level. So a higher privilege level will preempt anything that's running at one privilege level to run a handler. So you can preempt a running handler in supervisor mode, for example, by an interrupt coming in at machine mode to run something. So basically, at any level you're running at, the privilege acts as a mask over the lower privilege one's interrupts. Now, when you get an interrupt, one thing we changed around in going from the previous version of the privilege spec to this one is we separated out the stacks at the different privilege levels. So now each of machine mode, hypervisor mode, supervisor, user mode, they all have a separate two-level stack of what was the previous thing doing before that level was interrupted. And this turned out to make things much cleaner in the implementation, the design. And so this enable stack is when you take a trap at, say, supervisor mode, you pop the previous interrupt enable up here so you can restore it if necessary, right? And the same for the privilege stack, which records the privilege level of the thing that was running before you took that trap. Now, one thing to realize is the different, this is supervisor previous privilege, hypervisor previous privilege, and master mode previous privilege. There is no user previous privilege, because if you took a trap in user mode, you must have been running in user mode. There's no reason to go figure out what mode was running previously. It will always be user mode. And similarly, in supervisor mode, it'll either be, you're either running previously in supervisor mode or previously in user mode, so there's only one bit of state there. Now, this is the full layout that's seen in machine mode. As you go up the privilege levels, some of these fields disappear and are not visible. You only can see the ones that are relative to your privilege mode at each privilege level. Okay. So that's how the interrupts show in mStatus, and the key thing is this thing about this is the global interrupt enable. Now, one thing also we changed going from the previous spec to this one is how traps are handled and how they're delegated to lower privilege levels. So by default, in the simplest system, all the traps just go to machine mode. You dive down to machine mode, and mCause is going to tell you which interrupt occurred, and then you can, if you need to, redirect the interrupt back up to a lower privilege level. And you have to basically manipulate those bits in the status register such that when you do a return, it will appear as if you trapped straight to that event in the lower privilege level, right? So it's just a bunch of manipulations you need to do. It's actually not that costly. It's sort of a couple dozen instructions to set this up and then do the return. But the reason we moved to this model is that we decided that it's important to support just in hardware interrupt handler delegation. As Andrew sort of posted on the list, this stuff actually turns out to be very cheap to implement in the hardware compared to what we had before. And the idea here is now, at any level, you can delegate interrupts to the lower privilege level. So you're saying, I don't want to bother with this at machine mode. You can go directly to supervisor mode and have it service the trap at that level. So the interrupt delegation register has the same layout as interrupt pending and just says for each of those sources of interrupt there, will it be delegated up? And the model is that any privilege mode, you can delegate to the lower modes. Those lower modes, in turn, can then delegate to an even lower mode. So machine mode delegates to hypervisor mode. Hypervisor mode can choose to delegate to supervisor mode. Supervisor mode can choose to delegate to user mode, any one of these interrupt or trap values, right? And once you delegate it, the higher privilege mode is not affected by the settings of its local interrupt enable bit for that interrupt. It's handled only by the lower mode. Okay, so going back to this, So here's the story again. There's these hearts. They have 4 modes, local interrupts and external for each level of the stack. And here's the PLIC at the center of things, doing the routing of external interrupts to these global interrupts. Okay, so this is in the privilege spec. I just want to show this diagram. So I want to emphasize this is a conceptual block diagram. It's not meant to represent an actual implementation. It's just meant to help people understand the spec of this PLIC. The PLIC itself may be, you may implement it in a way that it takes many cycles to make a decision, or it may do multiple decisions in one clock cycle. That's kind of irrelevant. What we're really trying to show here is conceptually how the PLIC operates. So just to flow things through here, you have external interrupts come in, and they're processed by what we call a gateway. And the purpose of the gateway is to hide the differences between different ways of encoding interrupts, whether you're level triggered, edge triggered, message signaled. That's kind of handled by the gateway. The important thing is, at some point, you realize that I want to generate an interrupt request that's going to go into the PLIC and need servicing, right? So that's the gateway's responsibility, and we kind of abstract away differences between interrupt sources through the gateway. Okay. So the PLIC will then accept a request, and we'll get to when it can accept a request, and set the interrupt pending bit at the interrupt source. Each interrupt source can have a priority, which can be a machine writable register, so you can have runtime variable priorities. This is important for embedded systems, not so much for high-performance Unix systems, but embedded systems, like I said, often want to do task scheduling inside the interrupt controller. So you can set a priority here, and basically, so that the columns of this diagram are the different interrupt sources. The rows are the different interrupt targets. And each of those targets is one of those external interrupt lines going to one of the privilege modes on one of the hearts, right? So for each of those interrupt targets, you have interrupt enables indicating for this target which interrupts does it want to hear about. And in each case, it wants to hear about the highest priority interrupt that's pending for that target. Okay, so you're going across. So you're conceptually taking the max of all the enabled interrupts, and then if there's any that are above a threshold, so another control register in the PLIC is which is the lowest priority threshold for which the target wants to be interrupted at this point in time. So you can set a threshold. I don't care about interrupts at this lower priority. I just want interrupts above that. And you can use that to, for example, if you go to sleep mode, you can only wake up for certain important interrupts and not for less important ones. And at some point, this interrupt notification will be transmitted to the heart. It'll be interrupted. And then the heart will come back to the PLIC and claim the interrupt, and then recover what was the ID of the maximum priority heart at that point in time. Okay, so this is the whole flow of things through the PLIC at the core of things. So these gateways, like I said, they just convert from external interrupt formats to the internal format. And this is really just to abstract away the different kinds of interrupt sources, level, edge, message signaled, whatever. There'll be future ones in the future, I guess. Now, one detail about this is that you will not forward a new request to the PLIC core until the previously run handler has signaled completion. So the model here is once you run a handler, you assume that's atomic, and you don't want to run a second handler for the same device until the first handler is completed. Now, the completion goes back to the gateway, not to the PLIC core. So you tell the gateway, I'm done with the handler, so that the gateway can now inject a request for a new interrupt. And particularly for level triggered interrupt sources, the idea is if the level is still asserted and you send a completion message to the gateway, it will generate a new interrupt request because that device still needs some further service, right? And if it's edge triggered, the completion would just enable it to send in the next edge to the PLIC core, okay? So that's how we handle level triggered interrupt sources in the system, right? So the completion request enables a new interrupt if a level is still asserted into the PLIC core. So each interrupt has an ID, which one is it, and a priority, how important is it? So the interrupt IDs are integers from 1 to n. ID of 0 means no interrupt. And the priorities are integers, and larger numbers are higher priority. So priority 0 means never interrupt, right? If you set the priority on a source, it's effectively the same as masking it off. So now in an implementation, this is a template for all PLIC designs. In a given implementation, you can actually choose to hardwire the priorities. For example, the degenerate case, you just hardwire them all to 1, in which case the ID, there's a fixed ordering that lower IDs have higher priority. You might ask, why the interrupt IDs go with lower being highest priority and priorities are higher is priority? And it goes back to this diagram. If you made them both go the same direction, the diagram would be harder to draw, right? So if you don't believe me, go try doing it. So, lower IDs have higher priority, higher numeric priorities have higher priority in deciding breaking ties. But all these are parameterized. We're not saying how many bits you need to have in a priority register. These are all what we call in RISC-V land write any, read legal fields. You can find out what's available just by trying to write things and seeing if you get the value written back, right, for those fields. Okay, so the per target information stored in the PLIC core, you have a vector of interrupt enables and a priority threshold. So only those interrupts above that threshold will be signaled to the heart. And the threshold, if you set it to 0, has no effect. So in a simple implementation, you may not want to implement this feature. You just hardwire it to 0, and it just isn't there in effect. If the software running sets it to max pri, you've effectively masked off all the interrupts in one go. So now these interrupt notifications, if there's an enabled interrupt above 0 priority, above the threshold, then there'll be an interrupt notification sent to the heart. How long that takes is undefined. There'll be some bounded time in a system. But this allows, for example, that notification to be transported over different kinds of fabric. It doesn't necessarily have to be hardwired in one cycle. It can take arbitrary time to arrive at the destination, at the target. So just to recap and show this again. So these notifications here, once you determine there is an interrupt, this will be somehow communicated to the heart, some bounded amount of time in the system. Now, the important thing here is that these, when you receive that notification, you're going to claim, the interrupted heart is going to claim the interrupt from the PLIC by reading a memory map register. And there's no guarantee that when you go to claim it, the thing that caused you to be interrupted is still there, right? Some other heart may have woken up earlier than you and claimed that interrupt before you did. What the PLIC is going to do is when the claim arrives at the PLIC, atomically give you the highest priority interrupt that's pending for you and clear down the interrupt pending bit, right? So you may just go to see it and you find out there's nothing there because somebody else beat you to it, right? And then at that point, the PLIC core is giving you the interrupt. You then run the handler and just signal the gateway when you've finished. So this is kind of the operation of the PLIC core itself. And all of you familiar BlueSpec will understand how I'm writing this. This is just a set of atomic actions that the PLIC core has to do. There's 3 main operations: write registers, accept request, and process claim. So write registers is you're changing one of the settings inside the PLIC core. So you dequeue a write register request, you change a priority, or you change a threshold, for example. The accept request is the PLIC core sees there's a request for an interrupt pending from outside, and it will, only if the bit is clear, accept a new one and reset the bit. And the final one is to process a claim. When a heart requests an interrupt claim, it will atomically receive the highest interrupt and clear down the pending bit. So again, this is the way the PLIC core is specified. So any implementation just has to appear as if these rules happen in some sequential order. Okay, so the flow of an interrupt now, if you look at the whole system, how it works. So you have an interrupt source here. There's signaling interrupts to the gateway. The gateway is, when it finds the first one, it sends a request to the PLIC core. And notice it's not going to send any more requests until after the handler is completed, right? So the gateway is not going to attempt to send new things into the PLIC core. So PLIC core evaluates this, sends a notification to the target. The target claims the interrupt, receives the response, runs the handler, and sends back the completion. Right? At this point now, the gateway is able to send in a new request to the PLIC core. Okay. So, so we support preemption and nesting, and this, for the standard RISC-V systems, this is done because you have those 4 privilege levels, and a higher privilege can always preempt a lower privilege interrupt handler, and that's where we do preemption and nesting. If you're building a embedded system, you may want to do even more nesting, and in that case, you just add more hearts or more heart contexts on the output of the PLIC, right? So that's the way we would design it to support nesting. So access control. So when you're supporting this on systems, you want to only allow hearts the right privilege to access this stuff. The PLIC registers, the memory map, platform specific. So machine mode is the only thing that can access the enables and the priorities, and lower privilege modes can only access the claim, completion, and threshold registers, right? And you actually use the interrupt enables as a protection mechanism, you can only signal completion for inputs for which you're enabled. So that's the way you can give direct access to the PLIC registers to a low privilege mode while ensuring it doesn't mess up the interrupts for the other sources in the system. So one thing about the PLIC is it's memory mapped. And we didn't want to fix where it lives in memory because RISC-V is meant to be used in a lot of different contexts. A lot of platforms are going to have pre-existing memory maps that we cannot conflict with. So we left the specification somewhat open, but you actually need a concrete specification. So Sci-Fi, we put out a platform spec. It's available for everybody to look at. And this is just where we put the PLIC in the Sci-Fi Freedom platform. You're happy for everybody to clone this and use the same memory map layout if it fits your given platform that you're working with. Right, so we need a concrete mapping of that PLIC, but we didn't want to mandate a particular one because of this collision with existing memory maps. Okay, running out of time here, just want to go through what's the most important things to get across. Yeah, I think one thing about the interrupt and trap vectors, so by default there's a single entry point for interrupts and traps. And when people argue about this, whether you should have hardware trap vectors or not, it comes from these two camps. If you're in the sort of Unix camp, you treat interrupt as data. It's something that we put in a data structure and process later. If in the embedded space, you treat interrupts as control flow. This is the thing I need to do next, right? So you can support both of these by choosing to have more or less explicit entry points code out at MTVEC in the trap vector. So user level interrupts, we basically just extend the system up to user level. We had user CSRs and a user return instruction. Exactly the same scheme, it's just a natural progression of what we had at lower privilege levels. And the way we're thinking about using this actually is to enable secure processing in embedded systems where you have a secure boot, trusted kernel, and then you want to run an embedded application that wants to do interrupts and have low-level access, physical memory access. You use physical memory protection to prevent this from touching things, but now you can delegate interrupts straight away here, so you can have very rich embedded application functionality directly talking to interrupt devices while keeping a secure base and machine mode. That's the motivation for this user mode interrupts. Questions? Yeah, this is all a new spec, and these slides are also be on the lanyard and on the website.
Hey, Krista, Michael Pellauer from NVIDIA. Nice. So in a multi-core setup, do you envision sort of one PLIC per core?
No, the PLIC is the central agent.
So one PLIC in the system globally connected to one core?
That's right. There's one PLIC globally in a system. The main conceptually be one PLIC. You can actually implement it in a distributed way, but conceptually there's one PLIC.
But it's only each PLIC is only issuing to one core. Or sorry,
no,
the PLIC, because there's only one. It's only issuing to one physical core.
No, the PLIC is it has multiple inputs and multiple outputs that all happen concurrently. Right.
Hi, I'm Michael Broder. I'm unaffiliated. Is the multiple levels for these interrupts, is that the way you control the urgency of a task?
Yeah, I think this is something that needs a longer discussion, but a lot of systems want to just do the minimum in the handler and then prioritize scheduling outside the handlers. The low-end systems, you use priority to schedule what you do next. You can use preemption, I think, but I think in most cases you don't want to do that. But that's the way you would do it. You could add more hot contexts and fix the relative priority of those hot contexts to provide that scheduling.
All right. Thanks, Krista.
Thanks.